So all we're going to do is review really quickly what we went over yesterday. You already did some homework assignments on this, so here we go. If we look here, you can tell what I've got is this Bohr's model of the hydrogen atom. Now, why do you think it looks a little better on there? Why do you think this is a model of the hydrogen atom? I think it's the model of the hydrogen atom, Hannah. What would be special about a hydrogen atom? Okay, what number is hydrogen on the periodic table, Gabby? 1. So, Hannah, how many electrons does hydrogen have? So we're only dealing with one electron movement here. That's why this is called Bohr's model of the hydrogen atom. If we had a sodium atom, say, there would be 11 electrons. So if we were thinking about it heating up and cooling off, there'd be 11 electrons possibly moving, right? So here we're just dealing with one at a time. And all this says is if an electron falls from, say, the 5th ring of your Bohr model back to the 2nd ring, it'll give off violet light. If an electron falls from the 2, 3, 4, 4th ring to the 2nd ring, it'll get off blue light, right? Now, there are other wave photons of light that are given off that are not visible to us, okay? But many of them are visible. If we look at this right here, this is the gist of what we're talking about. This electron is falling back to its what? What do you call its innermost circle? What do you call an atom when all of its electrons are as close to the nucleus as possible? The atom is said to be in its blank blank. Anybody know?
Ground state.
Ground state. That's exactly right. So this electron's falling back to its ground state, okay? And this one here you can see is falling from N4 to N2. So you'll be responsible for making calculations of this by looking at the back of your reference tables. Now right here is the back page of your reference tables. And if you look, you can see we have Bohr's model of the hydrogen atom there. So that last little GIF that we saw showed an electron dropping from level N4 to level N2, all right? Level N4 is this ring, N, energy level 4, to level N2. So we'll go around, we'll say, oh, this is the one that goes from 4 to 2, from 4 to 2. So if we scroll down here, let's see, I moved it up here. The one that goes from 4 to 2, it gives off a photon that has a wavelength of what? 486 nanometers. That is equal to 4.86 times 10 to the negative 7 meters. So we keep going down here to the bottom, and we would realize that 4.86 times 10 to the negative 7 is just right to the right of the green-blue line. So that light will be right here. It will be a greenish-blue color. That is the gist of what we'll be looking up. And you did a worksheet on that yesterday. Another thing I'd like to review with you from yesterday is straight up the electromagnetic spectrum, okay? Here's the electromagnetic spectrum. I did a lesson on it yesterday, but I didn't make it an ad puzzle. So many students probably didn't bother to watch it, so I'm going to quickly go over the electromagnetic spectrum right now. The longest waves in the electromagnetic spectrum are radio waves, okay? And then ones that are a little bit shorter than that are called microwaves. Microwaves are what your cell phone runs off of, all right? They're just like radio waves, except for they're a little bit shorter, so they're a little bit more higher blank. Frequency, that's right. They're higher frequency because the wavelengths are shorter. So you can send more information in the same amount of time. Does that make sense? Microwaves go from being a meter long to being a millimeter long, right? A little shorter than microwaves. are what we call IR, or infrared. And those are just a little bit too long for you to see. And then right here in this magic spot is visible light. Okay, if we spread this out, we can see colors Roy, G, Biv. All right? The shortest wavelength of light that you can see is called what? The shortest wavelength that you can see. Which one of these is the shortest? Violet. And anything that's too violet or too purple or slightly too short a wavelength to see, you to see is called UV. A little bit shorter than that, X-ray. And a little bit shorter than that, gamma. Okay? Gamma, most dangerous. Gamma rays are the shortest, most dangerous rays. All right? Right? X-rays are such high frequency they go right through your skin and organs. They're only really hit your bones, right? And that's why we can take a picture of the inside of your body. Okay. Last thing to review from yesterday, and I'm making this quick. Last thing to review from yesterday. We talked about writing a shortcut for an Aufbau sequence. Let's think of someone like scandium. What position on the periodic table is scandium in, Cassie? What do you think? What position, if you're just going to name it with some letters and numbers, scandium? It's SC. It is just to the right of calcium. Uh-huh. Uh-huh. It's the first D. 3D1. Yeah, it's the third one over. You're almost there. 3D1. So scandium's in position 3D1. We know for scandium, the Aufbau sequence is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. But we can write it a lot shorter than that. What we're going to do is say all of this right here is really just the noble gas. Well, what noble gas is 1s2, 2s2, 2p6, 3s2, 3p6? Who's that? It's argon, isn't it? Right? So we're just going to say argon dash 4s2, 3d1. That is a noble gas shortcut. Let me ask you a question, Evan. What if you were going to write an Aufbau sequence for rubidium? For rubidium. Rubidium is Rb. It's an alkali metal. It's the 5th alkali metal. So what noble gas would you use to get to rubidium? What do you think the name of that is? Think about Superman. It's krypton. That's exactly right. So if we look up here, Rb, rubidium, we're going to write this. That's going to be very easy. Instead of writing all this stuff, we just go back to the last noble gas that we passed, krypton. So we write krypton, and then rubidium's in 5s1. And that's it. We don't have to do any more work than that. If we're going to do rubidium, that is equal to krypton 5s1. That's a lot easier to write than writing all those numbers, isn't it? So that's cool. Yesterday we learned a lot of shortcuts. The last shortcut I would like to review with you is a Lewis structure. Okay? Let's think about an atom up here. Let's think about this atom. Let's think about the atom silicon. How many valence electrons would silicon have, Isabel? 4. That's exactly right. And if you're at home and you're wondering why, the tall rows, all of these have one valence electron. All of these have two. If you're drawing a Bohr model, it'd make it very obvious. All of these have 3 valence electrons, 4, 5, 6, 7, 8. I often just call these groups 1, 2, 3, 4, 5, 6, 7, 8. Now, if you count the middle 10, this is group 13, 14, 15, but I just like to say 3, 4, 5. And a lot of chemistry teachers just refer to them like that. So if we were doing silicon, if we drew a Bohr model of silicon, it would look like this. 2, 1, 2, 3, 4, 5, 6, 7, 8, 8, and 1, 2, 3, 4, right? Silicon would be 2, 8, 4. But we don't have to do that anymore. We can just write silicon and just realize that it has 1, 2, 3, 4 valence electrons and just put 4 dots around it. That's how simple Lewis structures are. The last thing I want to mention about Lewis structures is I will not have you draw Lewis structures for these guys in the middle. In college, you'll have to learn to do this, but not in high school chemistry. So these guys you will not need Lewis structures for, all right? Because we don't know how many valence electrons they have yet. We haven't even gotten to there. All right, cool. Last thing, I want to talk to you about the trend in sizes for the periodic table, all right? If we are looking at the size of atoms on the periodic table, we would take a look at this graph, or just understand this graph that was created by Linus Pauling, all right? These are the atomic radii, okay? And this is just a comparison of all the atoms, all right? Now, if you'll notice, in which corner is the largest atom, Carlos? Which corner is the largest atom? Bottom left. And in which corner is the smallest atom? Top right. So that's the trend you need to understand. That's it. As you go down, you're adding more rings. Poof, 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 poof. As you go down a column, you get bigger. But as you go to the right, you get smaller. Does anyone remember why you get smaller? Anybody? That's right. As you go across, you're getting more and more protons. So there's a stronger magnetic pull, and the atom shrinks. Does that make sense? So knowing this trend, I can ask you to put these atoms in order. And I'm going to ask the people at home, this is our last question on your Ed puzzle. And that would be, place these atoms, I'm going to have y'all do it here, in order. Go from biggest to smallest, all right? I'm going to give you manganese, lithium, rubidium, oxygen, and hydrogen, all right? Let's put those in order from biggest to smallest.